Archimedes, considered the most important of the Greek mathematicians and of the whole of antiquity, lived in Syracuse, in Greater Greece, on the island known today as Sicily, in Italy. Many of the important discoveries in geometry made by Archimedes were achieved through the equivalence and equilibrium of physical models. We can imagine, for example, that he visualized a disk shape as being composed of concentric circles, extrapolating a model made with rope. By straightening the circles of rope, he could estimate and later prove that the area of a circle is equivalent to the area of a right-angled triangle whose longest side adjacent to the right angle is equal to the circumference of the circle, and whose shortest side adjacent to the right angle is equal to the radius of the circle. His ideas were so revolutionary that they influenced a large part of the mathematics still used today. Cavalieri, a disciple of Galileo and a professor at the University of Bologna, is famous for having set out, inspired by Archimedes, what came to be known as Cavalieri's principle. This principle is based on the conception of a flat area as a juxtaposition of infinite segments. Let's look at this rectangle made up of sticks. If we move any of these sticks, or segments, a new shape is produced, but the area remains the same. Cavalieri's principle states, therefore, that shapes which have transversal segments of the same length have the same area. Like these triangles, which are different from each other, but are formed from the same segments put together in different ways. They all have the same area. This principle also applies to the volume of solids, but here we no longer talk of length of segment, but rather of equal areas of plane sections. This is illustrated by this pyramid made up of slices. If we move these slices, we make a pyramid of a different shape, but the volume remains the same because the slices are the same, and therefore their areas are not altered. Cavalieri's principle was used brilliantly, yet intuitively, by Archimedes as a means of discovering the relationship between the volumes of a half-sphere, a cone, and a cylinder of the same base and the same height. Archimedes noticed that when we cut through the three solids at the same level, we obtain three slices, and the slice of the cylinder is always equal in area to the slices of the cone and the half-sphere together. He was inspired by the principle of physical equilibrium. Whatever sections are measured, the area and weight of the slices always balance. He concluded that the sum of the volumes of the half-sphere and the cone is equal to the volume of the cylinder. The volume of the cone is 1/3 of the volume of the cylinder, so the volume of the half-sphere can only be 2/3, which means that the ratio between the three volumes is of 3 to 2 to 1. It's easy to prove Archimedes' discovery in practice.